Two events which appear to happen at the same time for me do not have to be at the same time for you, not according to special relativity. Why not? Well, let's take a look as we explore the idea of simultaneity. We've seen surprising results to do with how time slows down and how lengths contract for moving bodies. Those are real phenomena and arise from the fact that the speed of light is constant for all observers. And there is one other crucial consequence of the fixed speed of light. Two observers will generally not agree when two events happen. For example, if one person says that two fireworks went off at the same time for them, then another observer somewhere else will not agree. The two people will not agree on what simultaneous means. Simultaneity is not an absolute state. It depends on where you are and how you are moving. So let's think about how we can work out what simultaneity means. Let's say Alice sees two fireworks explode at the same time. What that means is that the light from both fireworks is reaching Alice's eyes at the same time, so she perceives them to be simultaneous. But one firework could be further away from Alice than the other firework, and if the firework which is further away goes off much earlier than the nearer firework, it would appear to Alice that the light from both fireworks arrives to her at the same time just because the travel times and distances happen to be just right. In this way, Alice would see the two fireworks going off simultaneously, even though they are at different distances from her. But if Ben is also watching the same fireworks and he is equidistant from both, then for Ben, one firework goes off first and then a short time later, the other firework goes off. To Ben, the two fireworks do not explode simultaneously. This scenario shows a simple example of how two people do not agree on what being simultaneous means. In this example, both Alice and Ben were at rest, but the same disagreement about simultaneity applies if one observer is moving. So let us now work out the time difference that Ben might see for something which is simultaneous for Alice. Alice is in a train which is moving at constant velocity past Ben, who is static on a station platform. The train has a length L, and inside the train there are two identical clocks at each end of the carriage, with the green clock at the rear of the train and the blue clock at the front of the train. Alice is equidistant from each clock. Alice is holding a light bulb, and as Alice passes Ben, the light bulb turns on and both clocks start at the same instant. The light travels to each clock and each clock stops when the light hits it. When each clock stops, it shows a time, and the time is TG for the green clock and TB for the blue clock. Just so it's clear whose perspective we are looking at, in the top right corner there will be an A or a B to denote the person's frame of reference. So even though Alice is moving, as we know, she is allowed to claim that she is at rest because she is in an inertial frame of reference. Hence Alice claims she's at rest, and that means that the train, the clocks and Alice do not have any relative motion between them. So the light bulb goes off and the light travels towards each clock. But because Alice is equidistant from both clocks, the light takes the same time to reach each clock at the speed of light. And so Alice sees both clocks as showing the same time. Hence for Alice, the clocks always stop simultaneously, no matter if she is actually at rest or actually moving. Because if she's moving, she can still claim to be at rest. So the clocks are always simultaneous for Alice. Now, if we take the case that Alice is at rest opposite Ben, then from Ben's perspective, this is what happens. The light bulb turns on and the light travels to both clocks, and Ben also sees the clocks showing the same time. So for Ben, the clocks stop simultaneously when Alice is at rest. Next, let's take the situation which we started with, where Alice is moving at constant velocity past Ben. As Alice passes Ben, the light bulb turns on and the light starts to move towards the clocks. However, as the light is travelling to the clocks, the train is also moving to the right. Because the green clock is moving towards the light has to travel a shorter distance before it hits the green clock. And so the green clock stops first and the green clock shows a time TG. The train keeps moving and the light keeps travelling towards the blue clock. Because the blue clock is moving away from the light, it takes a longer time for the light to catch up with the blue clock. We know that the light will hit the blue clock at some time because the speed of light is always larger than the speed of the train. Nothing can outrun light. So the light hits the blue clock and the blue clock stops showing a time as TB. So it is clear that as long as Alice is moving, Ben does not see the clock stop at the same time. And for Ben, TG is always less than TB. The clock's stopping for Alice was a simultaneous event, but for Ben it is not simultaneous if Alice is moving. What they see from their own perspectives is not what the other person sees. The only time Alice and Ben agree on the clock stopping simultaneously is if both are at rest. As soon as Alice is moving, however, Ben does not agree that the clocks stop simultaneously. Let's calculate the time difference between the green and blue clocks that Ben actually measures. We know when the clocks start that the light bulb is a distance L/2 from the clocks. The green clock is moving towards the light, so the green clock's motion is reducing the distance that the light will have to cover. The distance which the green clock has moved before the light hits it can be called x. Now we know that the clocks start as the light is emitted and the clocks stop when the light hits them. For the green clock, this time is called TG. So we can see that the green clock has moved a distance x in time TG. Distance moved is speed multiplied by time. So x equals the speed of the train v times TG. Hence we can say that the distance the light travels to the green clock is going to be L/2 minus v times TG. But we also know that light travels at speed c, and so the distance light moves in a time TG will equal c times TG. These two distances must be the same, so we can say that CTG equals L/2 minus v times TG. We can then rearrange this expression to get an expression for TG, and this is the time which Ben measures for the green clock. This is the time when light hits the green clock. For the blue clock, the time when the light hits it is called TB. The blue clock is moving away from the light, so the blue clock's motion is increasing the distance that the light will have to cover. This extra distance the light has to travel is called y. As we did before, we can say that y equals the speed of the train times the time. So y equals v times TB. So in a similar way we did for the green clock, we can say that the distance the light travels to the blue clock is going to be L/2 plus y, which is L/2 plus v times TB. And light will travel a distance c times TB in this time TB. So we can then write CTB equals L/2 plus v times TB. Rearranging this expression gives us the time that Ben measures for TB. This is the time that the blue clock stops. We now have two times, TG and TB, so we can work out the difference between these two times from these two expressions. We will call this time difference delta t. It takes a bit of rearranging, but we can finally arrive at an expression for delta t, the difference in times between the green and blue clocks. Remember that this time difference means that Ben does not see the clocks stop simultaneously, even though Alice did see them stopping simultaneously. So Ben and Alice do not agree on when the two clocks stopped. They see them happen at different times in their own frames of reference, that is, from their own perspectives. The only time that Alice and Ben agreed on the two clocks stopping simultaneously was when both of them were at rest. In that case, they can be considered to be in the same frame of reference, both of them, and the clocks being at rest with respect to each other. But as soon as Alice moves, then Ben will not agree with Alice on when things happen, and Ben can work out how much time difference he will see from the expression that we have just derived. And one other thing to point out, which you might be wondering about, the effects of time dilation and length contraction, which Ben experiences for Alice's moving frame of reference, are already rolled into this expression for the time difference. We don't need to worry about those effects separately. In the real world, let's say there were two clocks at either end of a long bullet train, and both clocks stopped simultaneously for Alice, who's on the train. What would Ben see from the platform as the bullet train sped past him? Well, if the train was 100 metres long and moving at 200 kilometres per hour, then we can calculate that Ben would see a time difference between the clocks with lots of zeros in it. Such a tiny time difference is not discernible to the human eye. So this is why Ben will sense the events as being simultaneous, but in reality they are not. So just like with time dilation effects and length contraction effects, we cannot experience these tiny differences in simultaneity in our everyday lives, just because the speeds things move on Earth are so much lower than the speed of light. Even if our bullet train was somehow moving at 50% of the speed of light, then Ben would measure a time difference of only about 222 nanoseconds. But this would still not be noticeable with the naked eye, even for the train moving at half the speed of light. So the speed of light being constant leads to the conclusion that two observers will not agree on the sequence of two events. What each one sees will depend on their relative motion with respect to the events and each other. They can only agree on two events being simultaneous if they are in the same local frame of reference, i.e. the same location. But as soon as one observer is moving relative to another, then they will not agree on when things happen and in which order. This is one of the unusual consequences of the special theory of relativity. We've shown some of the basic concepts of special relativity, which Einstein proposed in 1905. Things like all motion is relative, the speed of light is constant for everyone, and how observers experience time and space personally to them. In the next video, we will complete our look into special relativity when we see how Einstein derived his most famous equation, E = mc². So until next time, keep thinking physics.